All right, foundations of Math at 11. Here we go. We are looking at, as promised, normal distribution. So the normal curve. Okay, now I showed you the image on the standard deviation video, so we're going to look at it again. This is the normal curve. It's a bell-shaped curve that's symmetric about the mean. All right, and we talked about this briefly in the last one, but everything underneath is a percentage because there's a probability of your data occurring. And all of that percentage adds up to 100%. So all the possible events that can happen, the probability of any potential events, so test score or whatever other data we are looking at, will be somewhere underneath our normal curve. The standard deviation is related to it because, as you can see by this image, the further your standard deviations get away from your mean, the more obscure, the more rare your data becomes. Most of the data here, 68%, is located within one standard deviation of the mean. So the normal curve is going to provide us a ton of detail. Now here's an example of two normal curves. So the same curves, the only difference is they have different means. So they're just shifted differently along a given axis. Here's another example of a normal curve, but as we mentioned in the standard deviation video, with different standard deviations. So just because your normal curve doesn't have the exact same shape, with respect to, like sort of a stretching or a squeezing in, it doesn't mean it changes the dynamics of that curve. This just means we have a smaller standard deviation. So our data is more crammed together, but it still has the same spread with respect to standard deviations from the mean. So what we have with calculating the probability underneath is something called a z-score. And what we do is we take our normal curve and we end up calling it the standard normal curve. And what we do is we take those percentages away. We write everything with respect to a mean of 0. So here mu is 0, and we're moving just 1 or 2 standard deviations away from the mean. So there's 1 in either direction or 2 in either direction, and then it fits the probability score on our Z table. Now, I've given you a Z table in class. You can Google a Z table on the examples we're going to do here. I have some imprints of the Z table, and it has done all the hard work for you, and it's about finding the information in that table with respect to the data we have given. So for our Z score, we have a given equation, and the Z score equation looks like this. So it gives us the probability of where our data can be found, but always to the left. And you'll see what I mean by that when we do a couple examples. Now, how do we calculate our z-score? So here it is written. A lot of people just glaze over that. This is the important part. It's whatever given data piece we need. So x is a particular score we care about. Mu is our mean. And then we have our standard deviation. So you calculate that ratio to get your z-score, and then we use the table to find the probability, which is within the table. So here's an example. This is a snippet of a z-table. You can see the column here, I won't use yellow, the column here is your z-score, but only to the tenths. And then the row here increases our tenths. So if you think about it, just as a quick example, if I wanted to know where 0.42 is, well, here's 0.4, and then that's 0.0404142. So that would be 0.42, and that number represents 0.6628, which is 66.28%. That's how you read the Z table. We're going to do that now in live action. So in this question, and in most of the questions you'll find in here, you are given the standard deviation and you're given the mean, because we've already know how to calculate those things. Let's not make you do that again and again and again. So the example here, the question here is, if IQ scores are normally distributed with a mean of 100, okay, mean of 100, and a standard deviation of 15, all right, then determine, here we go, first piece we need for our z-score. Then what is the z-score for an IQ score of 120? So remember that our z-score is equal to our desired value minus our average divided by our standard deviation. So in this case, our desired value is 120. So 120 minus 100 all over 15. And if you solve that through, you get the ratio, the fraction 4 over 3, which simplifies to 1.33 repeating. But we'll stop after 2 decimal points. So this is the value we're trying to find in our table. Now the equation, just to clarify this for part B, because we now want the probability, is that we say the probability that x is less than or equal to 120, because that's the score we care about. The z table is going to give us the probability of everything less than that or equal to it, is equal to the probability. I'm just going to erase this now. I'll just keep our z-score value because I need the room. So our z-score value was 1.33. And we get the probability that z is less than, and you'll recognize this, the equation we just solved, we say is equal to the probability now that z is less than 4/3 or 1.33. So this is what we're about to find. So yes, we have a less than or equals here, but now the table is going to give us strictly less than. So that's the value we need to find. Where is it? Well, we need 1.3, so we're here, and then 3. So we're going to cross all the way to this one, because that's 1.3, and then 3. So we get that probability. So the probability we get is 0.9082, which is a percentage. So we multiply that by 100, and we get 90.82%. All right? But okay, now what does that mean? Right? It means, I understand the irony of saying the word mean all the time, that on our normal curve, if our mean was here, right, our average, our mean is 100. It means that 90.82% is to the left of the score we were given. So if 120 is here, we don't now concern ourselves with the standard deviations we were away from it. We just concern ourselves with the fact that all of these data points here represent 90.82% of the data. So what you could say is 90% of the participants, of the students, of whoever took this test, have an IQ of less than 120. All of the participants on this side, then, of our data give us the remaining 9.18%. So the Z table will only ever give you the left side. In order to find the right side, you just do 100% minus whatever percent you got, and you'll get the data that is represented on the right, what we call the right tail, or the right side. So that is what the Z table tells us. So let's look at another one. So a provincial math exam, which, I mean, yes, we have numeracy exams, but they're definitely not the same as they used to be, has a mean score, okay, I'm going to write this down on the top left, has a mean score of 68, and it has a standard deviation of 13.2. Now, we're being told that 30,000 students take the test. We're not overly concerned with that number just yet. A score of 49 or less fails. How many students fail the exam? Now, me, as an optimist, I don't really like talking about how many students fail. I'd rather focus on how many students pass. And we will see we can actually do that at the end of this. But we've got to focus on the left side of the tail, which in this case actually includes the fail side. So first, let's find our Z value. So we're setting up that our probability when x is less than or equal to 49 is equal to the probability that our Z is less than, remember, my given data value, so 49 minus 68 divided by my standard deviation. which gives me a probability Z is less than negative 1.44. And yes, you can have negative probability or negative Z table values, 1.44. So where do we find that on our table? So negative 1.44, well, here's negative 1.4, and then we're going to 1.44. So we get this value right here. So we come out with the fact that we get 0.0749. Now that's going to be a percentage, right? It's about 7.5%. 7.49%. But now the question says, how many students will fail? So if 30% of the students, if 30,000 students take the exam and 7.5% fail, well, we just take 30,000 and we multiply it by that 7.5%. And what we end up getting is, we get the number 2,247. So again, if we had a normal distribution, right, and we wanted the probability of who's going to fail, it's only going to be 2,247. It's a very low probability, right? It's about 7%. So you could say, maybe it's like here. And it just takes into consideration that small amount of people, that 7.5% of participants. So if I said, if you wanted to be an optimist then, how many people passed? Well, you take your 30,000 and you subtract that 2,247. And that way, you get the positive side of the story. 27,753 people pass. So this side of my normal curve, the right side, represents the rest, 27,753. So that is the Z table and the Z scores. Remember that the Z table will only give you the left side, but you can find the right side by subtracting from it. So now the last thing I want to look at is working backwards from the Z table. If you're given a percentage or you're given a probability, then you're going to be working inside the table. So how does that work? The GPA at Vic High is 2.6. Now all of these scenarios are fictional, so bear with me. So the GPA is 2.6. So what do we get? We have a mu of 2.6. The standard deviation is 0.5. Now in this case, the top 10% of all students are eligible to attend UVic. Now again, not necessarily real, made this up. So top 10% of students, we would say, okay, let's say here, that represents my top 10%. Well then my Z table is going to give me this chunk. So my Z table is going to give me 90%. And 90% is 0.90. So what is the minimum GPA required to attend the event? So in that case, what we're looking for is we're looking for this. We have this information already, but we know that the Z value we call the Z inverse is 0.900. What Z score, right, is equivalent to 90%. We can find that. We know the standard deviation and we know the mean. So we have this set up, 0.5. Now we're looking for this number, but we need to know how to find this in our table. So rather than look down the Z column, we're not looking for the Z score right now. We don't have the Z score. We need the corresponding Z score for 90%. So you're actually looking in your table. So like here's 50% in your table. Here's almost 60% in your table, right? Here's just over 70% in your table. Here's just about 80% in your table. Here's 82%. So you're looking for 90, right? And you can see it ticks up. And here we have 87%, 87%. Okay, we go a little bit further. Oh, there's 89%. And there we have 89, 97. And then after that, you have that row is over 90. And if I cut off the table, if you'd gone one further, you would be just over 90%. And we can't be over 90%. We can be just below it, but we can't be over it. So this is our winner. This one is our winner. Okay, that is going to be the probability that relates to our Z score. So then we run it backwards. What's our Z score? Well, Our z-score is all the way over to here, 1.28. So we get 1.28. And then we just hammer off a little bit of algebra, multiply both sides by 0.5 to isolate the x, and we get x minus 2.6 equals, I'm going to go to green here so you can see it, 0.64, and then we add 2.6 to both sides, and we get x equals 3.24. So you need to have a minimum GPA of 3.24 in order to go to UVic in this lovely hypothetical scenario. But when in doubt, write a really good introductory letter and volunteer and just be a good human being with pretty solid grades, and I think you'll be okay. Don't stress yourself out with 98%, but hey, no one ever complained about 98%. All right, thanks so much. That was normal distribution. The last thing we'll look at in our stats section is confidence intervals. What does that mean? How can you be so confident that your data is accurate? A lot of times you'll hear give or take 1 or 2%, 5%. That's what we're going to look at next. Thanks so much. I'll see you next time.